Today we will be observing the difference between the motion of two falling objects with similar mass but different drag coefficients, displaying the effects of air resistance due to the object's varying shapes. The first object is a rolled up ball of paper towels, and the second is a flat laminate sheet. To begin, we need to understand the physics behind the motion of a falling object. As an object falls to the ground from rest, it does not have a constant velocity. It is actually constantly changing throughout the duration of the fall until it reaches the ground. Now, what are all the forces acting on the object? Or, in my case, the ball of paper towels and the laminate sheet. The first is the force that the Earth exerts on an object as it falls. This is called the gravitational or weight force on an object. It is equal to W equals mass times gravity, where the gravitational constant is equal to 9.8 meters per second squared. This is the force responsible for actually pulling the object to the ground. The second force acting on the falling object is the drag force, also commonly known as air resistance, which is the force of the air up on the objects as they fall towards the ground. This is equal to the force equals the negative drag constant times the velocity vector. So now that you understand the physics behind this lab, I will explain what I've done. For my experiment, I chose to drop two different objects in order to display the effects of the drag force on different surface areas. The first is a ball of rolled up paper towels, as you can see here. And the second was a laminate sheet with a large surface area that I chose to drop. As you can see, I then modeled both of these objects in Tracker, and after this I later built a computational model representing these systems on VPython. So, first on Tracker, I prepared a video of myself dropping a ball of paper towels, set the diameter of the ball with the calibration stick, which was 0.083 meters. I then placed the axis to follow the object as it fell in the negative y direction. As you can see, I would tilt the axis just slightly to match the ball's path. This is most likely due to the camera being slightly off center when recording the video. For the center of the ball representing the center of mass, Tracker followed it and recorded the data as it fell to the ground. And the curved graph to the right displays the object's motion, which is accelerating as it moves towards the ground. And the second was the video of the laminate sheet following Tracker. This calibration stick for this one is set at 1.626 meters, and here you can see it falling to the ground. After all this, I began to work with the VPython program in order to create a computational model of the experiment. To start, I entered the initial information, such as the ball's mass of 0.0021 kilograms, its initial position and velocity, both starting at 0, and finally the time of 0 seconds. The gravitational constant is set to 9.8 meters per second squared, as the j-hat direction is 6 meters y direction, since this is the axis the ball is following. The drag force constant E resulted to be 0.000325 after a trial and error process was followed to obtain this value. In the wild, T is less than 0.601 seconds, the total time of my video. In addition to the gravitational force, the drag force equation is also entered into the VPython code, which is the negative of the drag force constant multiplied by the velocity of the ball and the magnitude of the ball's velocity. The net force is calculated to be the weight force plus this drag force. So here's the model of the experiment represented in the VPython code. First, the ball of rolled up paper towels, which is expected to have less air resistance because it's in the surface area. As you can see, the blue line representing the drag force increases as the object falls, whereas the weight force, represented by the yellow line pointing in the negative y direction, stays constant. And after updating the code with the data collected from Tracker, the laminate sheet, here is the model represented by VPython. As you can see, the drag force, or the blue arrow, increases to its maximum point much quicker, well before it reaches the ground in this simulation. So what does it all mean? Terminal velocity is when the force of gravity on the falling object equals the drag force, or negative b times the vector v times j hat, which is equal to negative mg j hat. The blue arrow reaching its max for the following sheet well before it did for the ball means that the Lambda sheet reached its terminal velocity much faster than the ball did, showing that an object with a larger surface area will be affected more by air resistance, thus causing it to take longer to reach the ground than an object with less surface area of similar mass. The drag force has significant effect when it comes to objects of varying shapes and surface areas. Thank you for watching, and this is my lab 5.